In this video, we are going to discuss the oxyacids of chlorine or oxoacids of chlorine. Generally, the halogen acids having oxygen, it is called as oxoacid or oxyacid. And the halogens are fluorine, chlorine, bromine and iodine. Out of these halogens, the halogens which are less electronegative than oxygen, they are able to form oxyacids. Here fluorine is more electronegative than oxygen, and therefore fluorine is unable to form oxyacids. General formula for the oxyacids is HXON, where X is halogen atom, preferably chlorine, bromine and iodine, and N is a number, ranges from 1 to 4. It can be 1, 2, 3, 4. There are 4 types of oxyacids of chlorine. Hypochlorous acid. Hypochlorous acid, in this hypochlorous acid, oxidation state of chlorine is +1. Actually, these 4 types are on the basis of oxidation states. In hypochlorous acid, oxidation state of chlorine is +1. Its formula is HClO. Value of N is 1. And when this hydrogen is lost, resulting anion is called as hypochlorite ion. Its formula is ClO-. Second type is chlorous acid. In chlorous acid, oxidation state of chlorine is +3. Its formula is HClO2. That is, value of N is 2. And when this hydrogen is lost, there is a formation of chlorite ion, which has a formula ClO2-. Third type is chloric acid, in which oxidation state of chlorine is +5. There are 3 oxygen atoms. Its formula is HClO3. And when hydrogen is lost, resulting anion, it is a chlorate ion, and its formula is ClO3-. And fourth type is perchloric acid. In perchloric acid, oxidation state of chlorine is +7. There are 4 oxygen atoms, that is, value of N is 4, and formula for perchloric acid is HClO4. And when hydrogen is lost, resulting anion is a perchlorate ion, which has a formula ClO4-. These are the 4 types of oxyacids of chlorine. Hypochlorous acid, where oxidation state of chlorine is +1. Chlorous acid, oxidation state of chlorine is +3. Chloric acid, where oxidation state of chlorine is +5. And perchloric acid, where oxidation state of chlorine is +7. Now, what are the trends in properties of oxyacids? These are the 4 acids: hypochlorous, chlorous, chloric and perchloric acid. So when we think about the thermal stability, hypochlorous acid, it is thermally less stable, and from hypochlorous to chlorous acid, thermal stability increases. So from hypochlorous acid to chlorous acid to chloric acid to perchloric acid, in this order, thermal stability increases. Second important property is acidic strength. Actually, according to Laurie-Bronsted theory, the acid is a substance which is able to donate proton, and the strength of acid depends upon extent of dissociation to produce a proton. So from hypochlorous to perchloric acid, ability to donate proton increases, and therefore acidic strength increases in the order hypochlorous acid to chlorous acid to chloric acid to perchloric acid. Here perchloric acid is strong acid, whereas hypochlorous acid is a weak acid. Next is oxidizing power. So among these 4 oxyacids of chlorine, hypochlorous acid, it is the strongest oxidizing agent, and as an oxidizing agent, their tendency decreases from hypochlorous acid to chlorous to chloric to perchloric acid. So perchloric acid is a weak oxidizing agent, or it has a weak oxidizing power, whereas hypochlorous acid, it is strong oxidizing agent, or it has a strongest oxidizing power. Now next important point is structure and geometry of oxyacids of chlorine on the basis of valence shell electron pair repulsion theory. On the basis of valence shell electron pair repulsion theory, geometry of molecule depends upon number of bonding pairs and lone pairs of electron present at the central atom. So in a molecule, central atom is attached to different atoms by means of bond, and the electrons which are involved in the formation of chemical bond, and for the formation of single bond, there is a requirement of pair of electron, and this is called as bonding pair. And the non-bonding electrons, or electrons which are not involved in bonding process, I am talking about the central atom. At central atom, some electrons are not involved in bonding process. These are non-bonding electrons. They are also called as lone pair of electrons. And the geometry of molecule, it is decided by bonding pairs and lone pairs of electrons. According to valence shell electron pair repulsion theory, the lone pair repulsion, it is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. Now there are some steps involved to predict the shape of molecule. First important step is write the Lewis dot structure. Then find out total number of bonding pairs and lone pair of electrons. At the time of counting total number of bonding pairs and lone pairs, consider multiple bond as a single bond. Then most important step is find out the steric number, and steric number, it is equal to the number of atoms bonded to central atom. This is equal to the bonding pairs, number of atoms bonded to central atom, plus number of lone pairs of electrons available at central atom. So steric number, it is a sum of lone pair of electrons and bonding pair of electrons. Then predict the structure from the steric number. So we'll have some examples of type of different molecules. Consider the molecule of the type AB, where A is less electronegative and B is more electronegative. Now if steric number is 1 and A is attached to B, it means there must be one bond, it means one bonding pair, and therefore lone pair will be 0. Its expected shape is linear and approximate bond angle is 180 degree. For AB2 type of molecule, steric number is 2. Now this A is attached to 2 B atoms, and therefore there must be 2 bonds. Bonding pair is 2 and lone pair is 0. Geometry must be linear. Then if steric number is 3, for the molecule like AB3, again A is attached to 3 B atoms, and therefore 3 bonds are there. Bonding pairs will be 3, lone pair will be 0. Expected shape will be triangular. Bond angle is 120 degree. Now here another possibility is, suppose A is attached to 2 B atoms, whereas there is one electron pair. E is a lone pair of electron or non-bonding electronic pair. So as A is attached to 2 B atoms, bonding pairs are 2, lone pair is 1. Expected geometry is triangular. but actual shape is angular. So for AB4 type of molecule, steric factor is 4. There are different possibilities. AB4 molecule with 0 lone pairs. It means when A is attached to 4 B atoms, bonding pairs will be 4, lone pair will be 0. This type of molecule has a regular tetrahedral geometry with bond angle 109 degree 28 minutes. Suppose A is attached to only one atom, that is B, but there are 3 lone pairs of electron. So bonding pair 1, lone pairs 3, geometry will be distorted tetrahedral. Actually this will be the linear molecule. Then expected geometry is tetrahedral for all these. Okay, when steric number is 4, expected geometry is tetrahedral. So when there is a 1 lone pair and 3 bond pairs, expected geometry is tetrahedral. Okay, but actual geometry is distorted tetrahedral or trigonal pyramidal. If the type AB2E2, it means A is attached to 2 atoms and there are 2 lone pairs, expected geometry will be tetrahedral because steric number is 4. Similarly, if steric number is 5 and molecule type is AB5 and suppose lone pair is not there, it means A is attached to 5 B atoms, bonding pairs will be 5 and expected shape will be triangular bipyramidal with bond angle 120 degree and 90 degree. If A is attached to 2 B atoms and there are 3 lone pairs, then also the expected geometry will be triangular bipyramidal. Okay, here B atoms occupies the vertical position whereas the lone pairs occupy the horizontal places. Okay, and resulting molecule will be linear actually, but expected geometry is triangular bipyramidal. Similarly, for steric number 5, molecule may contain 3 atoms attached to central atom and 2 lone pairs. Expected geometry is triangular bipyramidal. Now when steric number is 6, molecule, example of molecule is AB6, it means A is attached to 6 B atoms. Here bond pairs will be 6, lone pair will be 0, expected shape will be octahedral, bond angle is 90 degree. Accordingly, when one lone pair is there or 2 lone pairs are there, there is a distortion from the octahedral shape. Okay, and if steric number is 7, then example of this type of molecule is AB7. In AB7, 7 B atoms attached to A, there is no any lone pair and expected geometry will be pentagonal bipyramidal and angle is 72 degree and 90 degree. Now when 6 B atoms attached to A and there is one lone pair, then bonding pairs will be 6, lone pair will be 1. So there will be distortion in the pentagonal bipyramidal geometry. Actually expected geometry will be pentagonal bipyramidal, but when there is a lone pair, then there will be the distortion in pentagonal bipyramidal geometry. So as one or more lone pairs are present, then regular geometry, it will be distorted. We get different shape. Expected geometry will be different and the observed geometry will be different. And when lone pairs are absent, then that particular molecule is having expected geometry like trigonal bipyramidal, octahedral, pentagonal bipyramidal or regular tetrahedral, etc.